Hello everyone, it's Ibrahim Abu Talib from Reservoir Solutions. Welcome to our workshop Machine Learning for Petroleum Engineers. Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services is technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic visibility studies, technical support for academic researchers, PhD and masters, assisting in writing technical papers and publishments, technical petroleum courses by industry experts, providing mentorship programs. Our instructor is Eng. Ahmed Abdel Gawad. He is a reservoir engineer at MPC South Abu Znima Company. He graduated from Faculty of Petroleum and Mining Engineering in South University with an excellent grade. He is a Python data analysis and machine learning developer. He has many certificates in machine learning and data science, like deep learning specializations by Coursera, Applied Data Science Lab by World Quant University. Our webinar rules. Kindly ask your question in the chat box, mute your mic and camera, fill in the form when we send in the chat to get our webinar certificate within 1 week. Join our Telegram channel for upcoming webinars and courses, and the link will be sent in the Zoom chat. Contact us via this mail and this WhatsApp number. Eng Ahmed, can you start?
Yeah, I can start. I'm sharing my screen right now. So can anyone confirm that he see my screen? Yes. Okay. So hello everyone. Thanks for joining today's workshop. Hope you will benefit from it at the end of the day. Uh, Actually, about the certificates that Engineer Ibrahim mentioned, I really don't care about certificates. Uh, Actually, you learn more about data science and machine learning when you get your hands dirty and you build your projects, your own projects. So, without further ado, let's jump into today's workshop content. So, the purpose of this workshop is to demonstrate some basic concepts of machine learning, how you can apply it using no-code technique, using a user-friendly software called Orange Data Mining. We will practice with very simple examples, so anyone can follow along. The content is about data science lifecycle, what is machine learning and its types, in a very overview. We will practice in a regression and classification problem using the software that I called Orange software. So from the beginning, what I will not cover, I will not go in details of any machine learning model, like I will not go explain what is ADA boost, gradient boosting, what is logistic regression. We will just use the model. I will not go in details about any concept. I will show the general overview and the general workflow, and we will apply exactly what I see in the PowerPoint in the practice using the software. Uh, just from the beginning, how many of you have worked with machine learning examples like build a machine learning model or have gone through tutorials? Just mention in the raise your hand or write in the chat. Okay, great. Uh, don't worry, this is a very very beginner friendly. So let's back to our main topic. We will cover what is data science lifecycle, what is machine learning, when and when not to do machine learning, and why you should learn Python. For the data science life cycle, data science contain many major sciences under its umbrella like computer science, statistics, machine learning, mathematics, and the most important part is the domain expertise. Actually, without any domain expertise, you cannot apply data science skill in your domain area. So any data science project start with a problem. So basically, you have a problem that you need to solve. You need to solve this through data science. So you need to collect data. This data can be structured data and unstructured data. After that, you prepare your data by cleaning the data so you have a high quality data set that yield an accurate and reliable analytics results. So we all heard about that concept, which is garbage in, garbage out. Actually, this applies in the machine learning. If your data is poor, then the machine learning output or prediction will be poor also. So you need to have this step is very important. So you need to have a high quality data set so you can build a machine learning model that its output is really reliable. And then you're gonna explore the data sets that you have, like perform statistical analysis, data analysis, visualizing data using different type of graphs to gain insights, KPIs, pattern recognition, and so on. And then you can share your findings in a form of dashboard to your supervisors, to your managers, and so on. And you can build a predictive model, which is machine learning model or a statistical model. So now here in this step, which is building a machine learning model, it actually follow three important steps. This step actually has no value without the previous steps. So you have a problem. You first need to collect the data that is relevant to your problem. And most of the tutorials, they will provide the data for you. So uh, actually, this step is what I can say is really underestimated in the tutorials. For data preparation, they can be in checking for any anomalies, if there is any missing data, if any typos in the data, and so on. So data science contain two main blocks, data and science. Without data, there is no data science, and in reality, data science and machine learning are just tools. You can learn data science and machine learning through tutorials, through courses, or from YouTube. But to actually apply this skill and this knowledge into your domain expertise, or to add a real value, you need to have a domain expertise. It's like I'm a reservoir engineer, you are a petrophysicist, you are a geoscientist. So you need to be a good reservoir engineer first before you can apply the data science skill effectively in your work. Uh, that is simply the data science life cycle. If there is, are there any problems until now? Uh, I see in the chat that there is problem in hearing me. Can anyone confirm he hear me clearly? so there is no problems. So it is your connection problem. For now, we will jump into what is machine learning. Uh, Machine learning contains three main subsets, which are supervised, unsupervised, and reinforcement learning. The supervised, by its name, there is a supervision in the workflow. The unsupervised, there is no supervision, and the reinforcement learning. You may hear about semi-supervised machine learning, which is basically a combination between the supervised and the unsupervised. But basically, these are the three main types. We will go through each one. So we will begin by supervised and then go to the unsupervised and then give a hint about the reinforcement learning. So now the following are focused on the supervised machine learning. Supervised, by its name, as I said, it came from there is supervision. This supervision came from the human. The human actually supervised the training process of the machine learning model. How so? We can explain it in the few next slides. I actually love to explain the concepts using the example. And this is the example that we will work through in the practice, which is predicting the production rates, which are the oil, the gas, and water production rates using the sensor data, the permanent gauge, which are the downhole gauge, pressure, the wellhead pressure and temperature, the tubing, the choke inside diameter, and the separator pressure and temperature. Using these readings, we gonna predict the oil, water, and gas production rates in real time. So the measurements are in real time. Before machine learning, what are the tools that exist to solve this problem? There is multi-phase simulators, Olga software, and many others. It is basically using the real-time measurements of the downhole pressure, the wellhead pressure and temperature, and all the measurements from the sensors, apply the thermodynamics, the physics-based equations, and so on in the simulation, and then predict the production rates for you in real time. So any change in the gauges readings converted into changes in the production rates. So in this approach, we have inputs, which are the sensor data. We have a program or rules, which are the simulator. And then it produces the output for us, which are the real-time measurements of the oil, gas, and water. But in the machine learning approach, how we can solve this problem, we have production tests dataset, like the production rates of the oil, water, and gas, and the readings of the gauges, like bottom hole pressure, wellhead pressure, wellhead temperature, separator pressure and temperature, and the choke size. Using this data, we're gonna build a model that will fit on this data, and we will use it to predict the oil and water and gas rates in real time. So in this approach, we have the inputs and we have the outputs. The inputs, which are the sensor data, the outputs, which are the production rates. We give it to the machine learning model. The machine learning model will be trained and it will give us the program, which is the model after training. It is a trained model. We can use this model for production. So we can deploy it in a software using the real-time measurements of the sensor data. It can provide for us the real-time measurements or the real-time estimation of the production rates. So this is basically the difference between the machine learning approach and the traditional programming. The traditional programming, we have inputs, we have programs that we coded ourselves to produce the outputs. In the machine learning approach, we have the inputs, we have the outputs, but we don't know how to correlate between them. We don't know the physics, we don't know the thermodynamics, we don't know anything. We actually have we have an actual data, an actual measurements of the inputs and the outputs. We will give it to the model and it will figure out the correlation between them. So this is the difference between the physics-based approach and the machine learning based approach in the virtual flow metering, which is predicting the real-time production rates. It uses like multi-phase flow simulation. It combines thermodynamics, fluid dynamics, and so on. It is calibrated on the production tests and it back allocated to the single wells. For the machine learning model, it is based on the sensor data only. Using the sensor data, you're gonna predict the production rates. This is a comparison between the benefits and the challenges in each approach. The physics-based it says in the challenges is the computational costs. Actually, in the modern hardwares, uh, they are not considered a challenge at all. But in the machine learning, at the other side, it has a very, very challenge, which is you need to have a large volume of data, a reliable volume of data, so that the model is produced and reliable outputs. So this is the model structure that we are going to build. We have the inputs data, which are the sensor data. We provide them for the model, and then we produce the output. It produces the output for us, which is the oil, the gas, the water rates. Now back to the supervised, we have shown the example. We have shown our problem, which is predicting the production rates. We have shown the model structure, what we want from it. So we give it the sensor data, give the production rates for us. But now for the supervised machine learning, how it works, we have an X, which are the inputs to the model, and they are called features. And we have Y's, which are the values that we are trying to predict. In our case, it is the oil, the gas, the water rates. We said that there is supervised because there is supervision, and the Y actually is the supervision in the topic here. So you can summarize the supervised machine learning in this formula. You have an X, you have an Y. You need to know like a transfer function that take the X from you and to reduce the Y. This is simply the supervised machine learning. According to the type of Y, the Y can be continuous variable, like the pressure, the rates, the prices, and so on. And it can be discrete variable, like the lithology, it is sandstone, it is marl, it is limestone, and so on. It can be a categorical variable, like it is 0, it is 1, it is 2. Basically, a discrete variable. So this is the general idea about the supervised. We have data that contain X and Y. We give it to the machine learning model. The machine learning model will train on this data. So now it is a trained model. It can map from the inputs to the label. Now we give it the inputs. It will produce the outputs for us. So the sensor data in this case is the inputs. The model trained is the function, and the rates are the labels. If there is, are there any problem? Until now, I see. Are we going to set slide? Get slides, inshallah. Okay. Are there any problem until now? So everyone understand what I said in the previous slides? I need to make sure that you are following along with me. Okay. Okay. Only three. Okay. Now let's get back to the machine learning workflow. We have data. We provide this data to a model to be trained on, and then we have a trained model. We use this trained model to for a specific task like prediction. But what is the type of this data? This data can take two main different types, which are structured data and unstructured data. The structured data, which is basically can be an Excel sheet. It has rows and column and predefined structures. Like the X, we call them the feature, and the Y we call it the target. The unstructured data can be the images, the audio, the text, and so on. So, what are the machine learning, the supervised machine learning steps? We have a problem, so we need to define probably the problem. We need to collect the data that is relevant to this problem. We need to process this data to have high quality data set that is reliable to give it to the model. We will give it to the model to train on, and then we validate or evaluate this model. So let's back to our example, which is predicting the oil, gas, water production rates. I need to ask questions to make sure. So can anyone tell me what is the type of this problem? Is it classification? Is it regression? Is it supervised, unsupervised, and so on? Please type your answer in the chat. Supervised regression, right? Right, thanks so much. Exactly. The problem here is a supervised machine learning problem. Why it is supervised? Because we have inputs and we have outputs. We have the sensor data and we have the production rates that the model that we need the model to predict. And why it is regression? Because the y, which is the target variable, is a continuous variable. The production rate is continuous, so it is a supervised regression problem. Basically, to make your model add value, actually in the real world, you need to build the baseline which already exists. Let's say we have a multi-phase flow simulator. The accuracy, let's say for simplicity, the accuracy can say the accuracy. Let's say the mean absolute percentage error of it is 5%, and we build a machine learning model that the error in it is 10%. Then what is the value of the machine learning in this case? It actually didn't add anything. So in order to make your work add a value, you need to search for the baselines or the already existing methods that is used to perform your task. If you can beat them, then your machine learning project is successful. Actually, many people don't consider this. So we have defined our problem, and now we are going to collect the data which is relevant and will help us to build our machine learning model. In our case, we have the data set, which is the oil, water, and gas as our target variables. The bottom hole pressure, bottom hole wellhead pressure, wellhead temperature, separator pressure, and temperature, and shock size. Actually, I have this data from machine learning for oil and gas book. It is actually a clean data set. We will not apply any pre-processing step. There is no anomalies, there is no anything. We will use it directly to build the machine learning model, but firstly, we need to understand the data. So these are our features, our targets, which is the oil, the water, the gas, production rate, and these are our features that we will provide for the model. Now we have defined our problem. We have collected our data set. We are going to make some data pre-processing, which can be dealing with missing data, dealing with irrelevant data if there is any outliers. We can do some feature engineering, like deleting features that actually didn't or do not contribute to the model prediction. We can add new feature from the existing ones. We can group features and so on. This is called feature engineering, dealing with feature itself, not the values. We can make data transformation like normalizing the data, converting the categorical data into numerical data, and reducing the dimensions of the data. We will talk about the dimensionality reduction in the unsupervised section. So in the data preparation step, we need to split our data into training and testing set. Why? We need to evaluate our model. We need to make sure our model is actually making a good job. So we split our data to like 80% of the data is a training set and 20% of the data is a testing set. We give the training data for the model to train on, and then we evaluate the model on the testing data set. You may see splitting technique like the other one, which is training, validation, and testing set. Actually, this technique is used for to make sure that the model generalize well. Skip this part. Let's focus on splitting into training data set to give it to the model to train on, and testing data set for the model to evaluate. So we defined our problem, we collected our data, we assume we performed data processing, we will split our data into training test set and a testing set. We will give the training set to the model, and then after the model is trained, we will evaluate it on the test set. But how can we evaluate on the test set? How is the evaluation work? Assume this is our training data. We have the X, which is the bottom hole pressure, and the sensor data. We have GY. We give it to the model, and the model now is trained. For the test set, we give the X to the model. The model will predict the production rates, but we have the actual production rates. So now we have predicted production rates, and we have the actual production rates. How can we evaluate what are the different metrics that we can use in this problem? Can anyone tell me in the chat? No one? Right, right. Didn't get the question. What are the different metrics, like the error metrics that we can use to evaluate the model? In this case, we have the predicted production rates, we have the actual production rates. How we can evaluate the model prediction in this case? What are the different metrics? This is for you, GM. Right, Matty? Absolutely, yes. If there is anyone? Anyone else? Okay. As Martin said, there is mainly three types, which is the mean absolute error and normalized quality indicator metrics. Actually, this is the first time I hear this. Okay, we have the mean absolute error, the mean squared error, the root mean squared error. The mean squared error is basically the difference between we have the actual production or the actual value, and we have the predicted value. We will take the difference between them, between each value, We will take the difference between them all. We will sum these differences and we will divide it by its count. So we have a mean difference between the actual and the predicted values. The mean squared error is actually the square of this metric, and the root mean squared error as in the equation. There is another metric which is actually a more reliable than the mean absolute error, the mean squared error, and the root mean squared error. Can anyone figure it out? A more reliable metric. Actually, accuracy, no, accuracy for the classification problem. We will cover what is accuracy in the classification. Did anyone heard about MABE? No one? Okay. MABE is basically stands for mean absolute percentage error. If let's say let's give an example. If we have the predicted value to be like 1000, this is the actual value or the predicted value, and the actual value is 900. But what if the actual value is like 500 and this is the predicted value and the actual value is 490. The difference between them is 100. But is this error comparable with this error? Can anyone understand the idea? Each one, the difference between them is 100, but actually there is a big difference between them. 100 from 5,000, 5,000 is actually, yes, yeah, absolutely. 100 from 5,000 is actually like nothing, but 100 from 1,000 is actually a big deal. This is the idea of the mean absolute percentage error. The equation is you take the difference between the actual, the predicted, and the actual, the absolute value, and then divide it by the actual value. So you need to get the percentage of the difference between the actual value. Are we by 90% error from the actual or 5% error from the actual, and so on. This is the idea of the mean. I'm gonna write it, mean absolute percentage error. You can search about it. So let's get back. We can evaluate our model in a visual way. So we have the predicted variable, we have the actual variable. Let's say we will evaluate the prediction of the oil production. We can draw the predicted value in the y-axis and the actual value in the x-axis. If the values are confined on the straight line, this means that the actual value is basically the same as the predicted value. So the more the data is confined to the straight line, the better the model is. This is basically the R2 square metric that Martin mentioned. But if the data are scattered along this straight line, this means the model is actually doing a bad job. This is a visual way. Thanks. This is a visual way of how you can evaluate the model visually. So we have defined our problem. We have collected our data. Assume we have done data processing. So now we have a training data set and a testing data set. We will give the training to the model to be trained and then evaluate the model on the testing data set. And we have show how you can evaluate. So If the model results is okay with you, so you can deploy your model in production. But if not, you're gonna repeat the cycle again until you are satisfied with the model prediction. This is the whole idea of the machine learning. Right now, I have discussed everything I need to jump into the software to work with this problem. So I need to make sure everyone has understand the workflow, the general workflow, and what is going on. So please tell me in the chat. It is not an outlier. Uh, it is the prediction versus the actual. You can investigate why the model predicted this value far along from the actual. You can investigate. Yes. I'm trying to explain everything that I will do in the software in the PowerPoint. So without understanding the PowerPoint, you will not understand what I will do in the software. I have shown everything that we'll do in the software, so make sure you are following along with me. Okay, 5 people. Is there is, are there any problems? Difference between model training and evaluation. Okay. Uh, for the model training, we give it the x and the y. We are telling him you have this is the x and this is the corresponding y. So figure out the correlation for me. So now after training, he figured out the correlation or the transfer function that we after it has been trained, we will give it the x and it will give us the y, the predicted y. So for the testing, we will give it the x of the testing dataset. So it will produce the estimation of the production rate for us. So now we have the predicted values and we have the actual values of the test dataset. We give it the x and we know the actual y. He predict the y. So now we have the actual y and the predicted y. We will apply our metrics like mean absolute error, mean squared error, root mean squared error, and so on. By using this metrics, we can evaluate our model. So if the mean absolute percentage error is like 2%, oh, this model is doing a great job, and so on. So is it clear? Or yeah, I wish I can spell it right. Is it clear right now? Okay. Now, without further ado, let's jump into the software. Orange. This is actually a very user-friendly, a very intuitive workflow that it's a piece of cake software actually. So now, here is the idea about this software. It contains everything in an object that is called widget. So this is a widget to load the dataset. This is a widget to transform the data. These are widgets to visualize the data. You have a widget to visualize the box plot. You have a widget to visualize the distribution of the data. You have a widget for each model. Okay, it is basically like widgets, and you connect these widgets with each other so you can build your workflow intuitively. Now let's load our dataset. In our case, which is the word rates. Okay. Now the dataset have been loaded into this widget. Now I want to see the data in a table form. So I drag a line. So I say data table. Now I can see the data in a tabular form. Here is the Q oil, the Q water, Q gas. Okay. And here are the bottom hole pressure, well head temperature, separator pressure and temperature, and the choke size. These are all the data sets that came from the book. Now we will try to understand our data. What are the different distributions of our data set? What are the correlation between the features and so on? Let's simply start with it's orange data mining, orange data mining. I will give you a link to download it in the WhatsApp group. It's an open source software, so anyone can use it freely. Now let's get back to make a scatter plot. Now we want to see the correlation between the the relation between the bottom hole pressure and the QoE. And we will be surprised by the shape of the data. Here the scatter plot says that with the bottom hole pressure increase, the oil production decrease. How so? So the data contain the bottom hole pressure, the wellhead pressure and temperature, the choke size, and the separator pressure and temperature. Can anyone figure out the feature or the variable that is responsible for this negative relationship between the bottom hole pressure and the Q oil? There is a question for you. I will give like 3 minutes for you to answer, or 2 minutes. 2 minutes is enough. Again, the question is, we have the bottom hole pressure on the x-axis, the Q oil on the y-axis. With increasing the bottom hole pressure, the Q oil decreases. How so? What is responsible for this relationship? Okay, okay. We can see that with increasing the choke size, the pressure is inversely proportional to the temperature. It is actually between the bottom hole pressure and the Q oil. There is no temperature in here. You can, maybe you mean the temperature of the separator, of the wellhead pressure. Okay, this is exactly you can here in the scatter plot add a more variable to understand your data. So you have the bottom hole pressure in the x-axis, the Q oil on the y-axis. Here I'm showing just the capability of the software for you to understand your data. So we can color our data using the choke size feature. So now we can understand with decreasing the choke size, the bottom hole pressure increases and the Q oil decreases. Function of the drawdown. This is actually a function of the drawdown. You thought right, but actually this data set is not collected in different time steps, so it is a function of the drawdown. And if it is a function of the drawdown, the bottom hole pressure decrease and the Q oil decrease, not inverse proportion. So simply for this data set, the choke size is the main reason for this relationship. Now, what if we want to see the distribution of each feature? Like to see the distribution of the values of the bottom hole pressure to see if there is any outliers. This is the bottom hole pressure. This is the wellhead pressure. This is the choke size. As I said, there is no any outliers here in the data. This is the Q oil. This is separator pressure and temperature. All the data are in unconfined range. There is no any outliers in the data. We can see the correlation between the features, the linear correlation and the nonlinear correlation. We can drag and make a widget for like correlation. To figure out the correlation between the features, we can see I can control the correlation. I can see the Pearson, which is the linear correlation. We can see a perfect positive correlation between the separator temperature and the wellhead temperature. We can visualize this on the scatter plot. Separator pressure and temperature. Wellhead temperature, separator temperature. Oh, this is basically a linear relationship. Okay. There is a positive correlation between them, but it is actually not linear. What captures this relationship is the Spearman. So now it is actually a positive one. It is a perfect nonlinear relationship between these two features. Now let's jump into doing the machine learning. For our data, we need to specify the features for the model and the targets. So we need to select columns. We can see that the features is the, let's actually give it back. You remember my previous work? We can see that the feature will be bottom hole pressure, pressure, wellhead temperature, separator pressure, choke size, and the P separator. And for the Y, we'll choose the QOA. Now, after selecting our features and our target, what we said in the workflow, we're gonna split this data into training and validation data sets. Now, let's go to data sampler. Data sampler split the data into like, we have 80% for training, and the remaining 20% for testing. So we can drag here, we can connect this data after the sampling to our model, maybe the random forest, and now the random forest is trained on the training data. We can control the connection between the widgets. Here I can see, take the data samples, the remaining data, which are the remaining 20%, which are the testing data sets. So we give it the 80% of the data, and now we are going to evaluate this model after it have been trained. So for the evaluation, we said we have the model and we have the testing data set. So we connect the model to a widget called prediction. This widget needs a model after it has been trained and a testing data set. We can see here, I can tell it, no, take just the remaining data, which are the remaining 20% for the validation. And now we can evaluate our model. You can see the mean squared error, the root mean squared error, mean absolute error, and the mean absolute percentage error, and the R2. Here is the model prediction and the model error. Okay, everything is clear till now. Yeah, it is open source and it is free. Let's finish the evaluation. So now we have seen the metrics of our model. We can visualize this by using a scatter plot. I tell him just use the x-axis to be the oil rate and the y-axis to be the random forest predicted oil rate. We can see that the points are nearly confined to a straight line with the R2 square to with the R2 or R square to be 99%, I guess. Uh, Now we have done what we have gone through the example in the PowerPoint. Here in the software. Is, are there any problem until now? No. So the workflow is clear. We have applied exactly what we have said in the PowerPoint here in the software with no code at all. So anyone have problems, just drop it in the chat. If we want to compare other models, that is exactly what I'm going to do next. Thanks for asking. Let's say now we have a random forest, but who told me that the random forest will be our best model? Maybe the gradient boosting and maybe the linear regression. QOL is the oil production rate from the separator. Okay. Okay. So now we are going to compare between different models. Here is the random forest to make it clear. I'm going to drop another model like gradient boosting, and we can see the connection is the data, not the remaining data. The data which represent the 80% of the data, which is the training data. We can add like linear regression. We can add actually a neural network. You can see the neural network is training, and now after the models have been trained, we are going to send them to the prediction widget and to evaluate all these models with the remaining data set, which are the testing data set. Now we can see the evaluation of different models. Let's filter on the mean absolute percentage error. So the least one is the random forest. Gradient boosting came next. This empty is actually the neural network. I need to name it ANN. And this is the linear regression evaluation. So now I have compared between four different types of machine learning model, and I can add as many as I can. Uh, Everything is clear. Thanks. Do anyone have a problem? For anyone who know the structure of the neural network, actually I can control the structure. Here I'm saying it is a two hidden layer neural network with 100 neuron in each layer. We can add like it is a three hidden layers with 150 neuron in each layer. So train, it will train a little bit harder, and then we are going to evaluate the model. If there is any significance, no, it is still doing bad. Okay, the random forest beats all the models. So now we have implemented our first example, which is predicting the production rate. Here is a quick tip. We have now estimated the oil production rate, but what if we want to estimate the gas or the water production rate? Let's take it here and put the water production rate, and it will simply do the same as we did for the oil production rate. We can see the model are trained, the neural network is training, and we can evaluate the model. But what is this? Yeah. I don't know why the mean absolute percentage error produces these values, but the prediction is pretty well using the random forest again. So this is our first example. Are there any problems or any questions for this example? We will move to the next one. So is it clear? Okay, I will assume it is. For the next example, which will be uh, predicting. This example is actually introduced by engineer Johannes. Is a very contributor in the field of oil and gas in terms of Python and machine learning. This example is actually predicting the lithology. Yes, you can make the data for multiple wells and you can use. So this is we're gonna predict the lithology, which will be sandstone, claystone, marl, dolomite, limestone, using the drilling parameters, which are the torque, the surface torque average, the pump stroke rate, the bit RPM, the pump pressure, the flow out, which is the mud flow out, the ROP, and the total gas and the weight on bit and the effective circulation density on the bit. So our features is going to be these variables, and we will feed it to the model, and we will predict the lithology. Uh, if there is any problems in this example, uh, the example is clear or not? As I will jump into the software directly. We have discussed the workflow. Can anyone tell me, please, if the example is clear or not? Uh, Here is a question. How you think this data is collected? What is the source of this data? What is the source of the drilling parameters and the lithology? How we can collect this data and use it to build a machine learning model? I will give you like 3 minutes to figure out where this data is collected. As it, oh, this is absolutely right. It is from the mud logging data. Thanks. Mr. Mohammed Al-Gharib provided the correct answer, which is from the model. From the model, you're gonna have the grading parameters, and you will have the lithology. So from the model, we can use this data to predict the lithology in real time, uh, drilling using the drilling parameters. So now let's jump into the software again. Here we'll have a new file. As before, we will have a data importer. We're gonna import our dataset. In this example is the lithology prediction. Here is the data. And here are all our features and the rows of our dataset. Okay, okay. As we did before, we can show the data in data table. So basically here there are like 30 features, but we will just work with those features, which is the torque, bit RPM, RV average, total gas, and ACD bit. So we will reduce our features from the beginning, like select columns, or let's keep it as it is. And now we will try to understand our data. But firstly, what are the distribution we can show what are the distribution of each lithology in our dataset. Are this dataset is biased toward the sandstone, like most of the points or the samples are sandstone or other lithology? We can choose this by distribution top, the by chart. We will show the lithology. I can change the variable here, but as I said before, it remembered my previous work. So it set the lithology by default. Now we can see that most of our data set is sandstone, and a little part of it is the dolomite and the limestone. The second measure is the marl, and then the clay stone. Is this gonna produce problem in the model training or not? Yes, I will, inshallah. Can anyone answer this question? Do the large significance between the number of samples in each lithology produce errors or make the training and the evaluation uh, biased towards some lithologies against the others? Was biased, exactly. It's simply, yes, imbalanced dataset can cause bias. Exactly, it is a highly imbalanced dataset. Most of the time, it will be biased toward the sandstone. It will predict most of our samples to be sandstone than other than minority classes, which are the clay, the dolomite, and the limestone. There is a problem called the imbalanced dataset. So now we have shown the distribution. We won't show the distribution of each feature. We can show the distribution of light torque. Mm, oh, there is values that is less than 1000, and there is values which are lower than what? 30,000. Okay. Now from this plot, what we can conclude? Can anyone answer? I really like the session to be interactive, so forgive me for all the question along the way. Yeah, yeah, there will be certification. It can be outliers, right? Uh, there is missing data, maybe, but there is no missing data in the original dataset. Maybe it is an outlier. Actually, I will leave it to you as a task to figure it out. So, what if we want to show the correlation between the features and each other, like we did before in the regression problem, or the correlation? It will actually do the correlation for the numeric features only, so we can see a perfect negative nonlinear correlation between these two variables. I don't actually know what they are. We can see all the different correlation between the features. Okay. what we can see again. Let's see the distribution, the box plot by different lithology. Box plot. No, this is the box plot for like the total gas. We can figure out if the total gas is actually a good predictor to our model or not by, like we say, what are the different box plot according to different lithology. Actually, we can see the total gas median value or the mean or the median is different for different lithologies. It can be a good candidate for the model as a feature. We can show the ROP. Actually, the ROP is actually a good candidate. We can show the ECD bit. Maybe we can show what is the other one? The torque. Actually, the features which Johannes used here are the best candidates of all the other features to train the model on. So now we figured out what our data looks like. Now we're gonna make select columns. We will use the torque, bit RPM, ROB average, total gas, Newton bit ECD as our features, and we are trying to predict the lithology. Next, as we did before data sampler, we want 80% of the data to be at training and 20% to be at testing. So we will give it to gradient boosting. We will give it to random forest. We will give it to logistic regression, prediction, and we will evaluate them. We provide the models and the remaining data set. Okay, here, take the remaining. Now we can evaluate the different models. We can sort by the F1 score. The best one is the gradient boosting, and then the random forest, and then the logistic regression. And here is another question. In this problem, which is imbalanced data set, do the accuracy is a good metric or not? As we showed before, the distribution of each lithology, in this problem, is the accuracy is a good metric or not? Yes, it is a good metric. Okay. Is there any other answers? Anyone? Just talk your answer. Is the question clear or not? No, it is. In this, we are evaluating our model. We showed that we have imbalanced data set, which the data set is biased toward the sandstone, which is the sandstone is the majority class here. In this case, is the accuracy is a good metric or not? No, because our model cannot predict the results for limestone, so accuracy is not a good indicator. Right. Exactly. So let's assume the following situation. The accuracy is simply the number of corrected prediction to the total number of samples. Let's assume this situation, the dataset is 90% of sandstone. And our model is just, we assume that any sample that we get, it is a sandstone. In this case, what is the accuracy of the model. The accuracy. I assume a situation like 90% of the data is sandstone, and our model is not random forest, is not anything. We just assume any sample that we get is a sandstone. In this case, what is the accuracy of the model? 90%, right? So by just simply saying that that any sample that I get is sandstone, we get a 90% accuracy. So in this case, uh, which is the imbalanced data set, the accuracy actually is not a reliable metric. There is more way reliable metric, which is called the confusion matrix. And you will see why they call it confusion matrix right now. Confusion matrix. This confusion matrix says that for the gradient boosting, we predict the accuracy of the prediction of sandstone is 95%, but 42% of the error prediction in the sandstone are actually a clay stone. The model actually didn't predict any clay stone, any dolomite, or any limestone. It actually predicted only sandstone and marl. And we can see the accuracy is like 100% in the marl and 95% in the sandstone. So although the evaluation metric, which is the F1 score and so on, and the accuracy is 99%, the model actually is not doing a good job for the minority classes. There is a problem with the confusion matrix. So you understand that now the confusion matrix. So again, any question? This confusion matrix is basically we have the predicted variables, the predicted values, and we have the actual values. We will compare the model predicted sandstone, but what portion of the predicted sandstone, and it was actually a sandstone. This cell represents the model predicted sandstone, and they were actually sandstone is 95% of the predicted sandstone. But 42%, the model predicts the clay stone as sandstone, and so on. For the marl, it actually predicted the accuracy in the marl is 100%. 100% of the data are the model predicted is as a marl, and they will actually a marl. This is simply the confusion matrix. Now we will explore the different models. They are actually the same. The logistic regression is doing good job in the clay stone and a little bit in the sandstone, but for the dolomite and limestone and marl, there is actually a main problem. Can anyone know a technique that we can solve this problem, which is a highly imbalanced data set? I guess Metin will know. A sampling method, exactly. Like technique SMOT, SMOT, which is oversampling. We oversample the minority classes just to make all the distribution of each lithology is the same. So we have like 100 sample of lithology that is sandstone, 100 sample is marl, 100 sample is claystone. So there is no bias toward any lithology over the other. When the percentage of the prediction is not acceptable, there is a window for good prediction. I don't actually understand the question. Yusuf, can you formulate it in another way? Okay. Unfortunately, in the Orange software, This technique, which is resampling method, like oversampling and undersampling, doesn't exist until now. Maybe there is add-ons that I didn't add or anything else, but they are not here right now. So in order to solve this case, in our example, which using the orange software, you need to resample your data outside the orange, and then you load them again for the orange software. This is simply the situation. We can add here the neural network to see if it is doing a good job. Still, sandstone marked claystone, but the might and limestone, the prediction is very bad. I will provide a resource for the actual project of engineer Johannes, and he used oversampling, which is SMOT technique. Here in the Orange software, there is no widgets to do this. So you can read the article. I will give it in the references. So now we have just implemented the second example, which is lithology prediction using the drilling parameters. We have shown some limitations of Orange. We have shown some examples like imbalanced data set and what this can cause problems in the model prediction and so on. So now, uh, are there any problems? So I will continue in the PowerPoint. Are there any problem in this example after we train the model? Actually, this based on the baseline that you are trying to beat. If all the existing methods, like the MABE, is the lowest one is like 10%, and you produce the model that is like 5%, that you are actually made a successful machine learning project. It depends on many factors. Uh, so is it clear? You cannot always reduce the error. There are some limitations. Is it clear, Yusuf? Okay. We have finished the second example. Now let's back to machine learning. We have shown the supervised machine learning. We have shown an example using a regression problem, like predicting the production rates. We have shown classification problem, which is predicting the lithology using drilling parameters. Now we will show some examples of the unsupervised machine learning. We will not implement anything here, but we will show the main idea. So the unsupervised, unlike the supervised, there is no supervision. And we said before that supervision is represented as the y variable. So here there is only y. In unsupervised, there are different type of algorithms. Each algorithm has a certain task to do. There is algorithms for clustering. There is algorithms for association analysis. There are algorithms for dimensionality reduction and so on. For clustering is basically you have a data set, a raw data set. You give it to a model, and the model will cluster these data set into smaller clusters. Like it combine the similar points or the similar samples into a cluster, and it will give it a code like 0 and 1. How we can use it in our domain expertise? If there is any petrophysicist here, it is like the lithology. You define the lithology in the open hole log. Basically, you can give the raw data set to the model and say cluster this data set according to similar points. and it will produce certain clusters like the 0, 1, 2, 1, 3. It will cluster each data point to a certain cluster. And now using your domain knowledge and your petrophysics knowledge, you know that this cluster show the behavior of sandstone, low gamma ray. There is crossover between the neutron and density. So the model interpret the sandstone as a cluster one. This is maybe limestone. This is the shale or the clay stone. I'm not a petrophysicist. So this is how you can use clustering. For dimensionality reduction mainly used to reduce the dimension of your datasets. Why you reduce the dimension of your dataset? You can reduce the dimension if you have like 100 plus feature, you can reduce them to like 10 or 5 features, or you can reduce the dimensions of your dataset to visualize them in 2D or 3D. Here is an example. If we have a bike in reality in the 3D dimensions, I'm not mentioning the 4D, which is the time axis. So these are the 3Ds. Here is the bike. If there is a way to project this bike into two-dimensional space and still preserve most of the information about the structure of the bike, here is a simple solutions. We can project it in this way, and we can project it in this way. But it is clearly that this projection reduced from the data or the bike sketch from the 3D to 2D and still preserve most of the information about the structure of the bike. So this is basically the idea behind dimensionality reduction is reducing your dataset dimensions to a lower dimensions and still preserve most of the information of your dataset. You may they interpret the information as the variance. You can hear the term which is like 2 or 3 features preserve like 90% of the variance in the original dataset. By dimensions, I mean the feature of the dataset. We can have like 10 features. These are 10-dimensional dataset. We can reduce it to a 3-dimensional dataset. The 3 new dimensions are calculated features based on the original 10-dimensional dataset. It's like the BCA one, like A times x1, B times x2, C times x3, etc., etc., and so on. For the reinforcement learning is basically used in many of the enjoyable or the most entertaining tasks like self-driving cars, robotics, gaming. It is actually based on here is an agent and here is an environment. You throw the agent in the environment and it will learn by a concept of punish and reward. If the model did a good job, you will give it a reward. If it did a bad job, you will punish him. This is basically the very general idea of reinforcement learning. So now, what is artificial intelligence? Artificial intelligence is the major subset which uh, devote to making machines think and act like humans. Machine learning is a subset of the artificial intelligence focusing on enabling computers to perform tasks without explicit programming, like making the machine learn from the data. Okay. The deep learning is a subset of the machine learning, which focused on different types of models, which are the artificial neural networks. For different approaches, there are 2 main approaches in the machine learning workflow. There is some folks focusing on the model and type of the model and the model structure and the algorithm. And there is other ones that focus on the data. I am with the other ones that focus on the data. Actually, as we said before, high quality data make high quality predictions and high reliable machine learning model. Poor quality data will actually, for any different model, the prediction or the model performance will actually not be as good as if we provide high quality data for it. So choose the approach that you want. Uh, Now I actually need a 5 minute rest. So are there any problems? I just need to drink some water. It will be like 2 minutes. If there is any problems, please type them in the chat box. Yes, yeah, as I said, it is free to use. It is an open source software. Again, approaches for machine learning and deep learning are the same. Yes, they are the same. If your problem deals with structured data or tabular data, just use the shallow models like especially the tree-based model, like random forest and gradient posting exactly, and uh, Alabust and this kind of machine learning models. But if your problem deals with audio, video, text, it is basically the deep learning task. Okay, if you are working with tabular data, just use the shallow models. Give us like a roadmap or some tips for beginners to learn automation. And you are welcome. Uh, uh, okay, okay, Yusuf. We will discuss this at the end of the session. Uh, Now let's move to the next topic, which is when and when not to use machine learning. Uh, I guess inshallah. Yes. When and when not to do machine learning. Basically, when not to use machine learning. Machine learning is not a solution for any type of problem. Okay, you don't need machine learning actually. If you have a problem with simple rules that you can code yourself. If you have the inputs and you know the equations, you know the rules that map from the input to the output, so why to use machine learning at all? Okay, but when to use machine learning, you can use machine learning when you cannot scale. Like if I am an experienced email classifier, like I see the email and I can recognize directly if it is a spam or not spam email. But how many emails can I predict in an hour? Like 10, 20, 100. Machine learning can predict them like 1,000 in 2 to 3 minutes or less than this with the current hardware. So you can use machine learning when you cannot scale, okay? And or you don't know the rules or the equations to map from the inputs to the outputs. So you just have the data with the actual values of the inputs and the outputs, but you don't know how to map from this to this. You don't know the equations. You don't know the physics behind or anything. So you just use the machine learning. So you use the machine learning when you don't know the rules or when you cannot scale. Actually, machine learning is not like this. So it's actually like if there is a problem that you need to solve, just say the magic words. Machine learning. It works like magic. It is not like this at all. Many of your problems actually will be solved using programming, using Python, using any rule-based approach without using any machine learning. So at this point, I want to explain why Python and why you want to learn programming. You can use Python to automate like daily stuff. You can make your own applications. You can make your own programs, and it's what why to say when we can show. There we go. It's not this. I will show you how you can deploy, let's say after training the model of the Lithology classification, how we can deploy it in production. Model deployment. Why it is taking so long? Let's say we have built the model, we have saved the model, and now we want anyone can use our model. So we deploy it as a web application, so anyone can grab the data, like data that we trained our model on, and let the user define the right columns for the right variable. Like this is the column that represents the total gas. This is the column that represents the ROP, and this is a column that represents the RPM. Speed bit, breaking bit, and torque. Let's say now predict the solution. No, it's not Orange software. We have to use Orange software. I'm showing you how why programming is very useful for you. What is the software you are using for deployment and where it is deployed. I'm using Python. This application is actually a Streamlit application. I can deploy the application on the Streamlit share, which is a server based on the Streamlit itself, or I can deploy it in any hosting service. So now, the model predicted our lithology. We have the readings of the features, and we have the corresponding lithology. And now here is a legend to tell us the yellow color is sandstone, this is clay stone, and this is marble. And this is being implemented with Jupyter Notebook. You can use Jupyter Notebook, but I'm talking about the GUI, an application with GUI that anyone can use. Okay, do you understand me? Okay. This is a GUI application that I can send you the link. You can open this application. You can upload your data, and you can define the right columns for the right feature, and then let the model predict the lithology for you. This is a way why you may want to learn programming and Python. Uh, Actually, there is another situation that I want to show you that I actually use in my real work, which is the jet pump. I guess they're taking so long before because of the sharing. Maybe start, start. Oh, now it is starting. This is actually a desktop application, like any desktop application that you use in your daily basis. Uh, this application I built for our real case in the company, which is jet pump optimization. What this desktop do, I already built a cross profile with modeling all the components in our well. Okay, now I am connecting with this cross profile. So I have a cross profile. I am connecting it with it using Open Server, and then I can calculate the operating point for all the pumps that are in my database. But why to do all of this? Because Prosper produces error outputs or error operating points in the jet pump calculation in many cases. Yes, you can get a recording. I will stop for just a minute. So now let's get back. Why I take the hustle of building all of this? We can't show why. Here is the pump intake pressure as the inflow performance. The and this is the pump. This is the VLB, and this is the line that represents the prosper for solving the system. Let's simplify the problem. We have the VLB, we have the pump intake pressure, we have the pump discharge pressure by prosper. We can see this line give us 477 as an operating point, which is actually wrong because this line gotta extend in this situation to intersect at 891. Actually, I modeled many uh, or more than one of our wells, and it produces errors in most of cases. So there is an actual real case situation why you need to learn programming so you can apply your ideas and perform the calculation of the jet pump separately from the Prosper, and I interact with Prosper to get the actual or the right operating point of the jet pump. Uh, this is a simple one of the projects, and I will provide the PPT for you. So this is a Medium article about production data automation. I built an internal system to fetch the data from the Outlook and then fetch our production parameter from the report and then save the report. All of this automated and it's run daily. This article is about how you can interact with Open Server and Prosper to make like multicolor simulation for a new well. There's an application about relative permeability, normalization, and denormalization. This is basically a Streamlit application, as the one I showed before. I'm just trying to show you what are the different types of projects that you can build if you are if you know programming or if you know specifically Python. Python is the piece of cake programming language. Are there any questions as I am about to end? If there is any other question, uh, any question? Thanks, Matt. Appreciate. Thank you.
Thank you. Thank you, Engineer Ahmed.
You are welcome, Engineer Ibrahim.
In the end of this workshop, we want to thank Engineer Ahmed on this interesting session. Actually, all of us benefited from it. Finally, we want to thank anyone joined for us in this session, and we want to confirm that you should fill this form of certification to obtain your certificate within 1 week, inshallah. We want also to confirm that our next course is based in modeling and applied geochemistry that will be held on 25 July. If you want to attend it, you can register in the link of registration, which we sent in Zoom chat. Thank you again and see you in the next webinar, inshallah.
Okay, thanks everyone for attending the session. I hope you benefit from it. So goodbye.
Thank you, Enjah. Bye.